Okay, thank you very much for the introduction, and thank you for inviting me to this conference. So I'm going to talk about some Fourier analysis. The title of my talk is Fourier analysis of equivariant equivariant quantum cohomology. Although I'm not a specialist on Fourier analysis. Anyway, so this is somehow closely related to a conjecture of Teleman, Konstantin Teleman, and also many other people as well. But so I'd like to in this talk, there are three talks. So first talk, I'm going to talk about relation between Fourier transformation of equivariant quantum cohomology and mirror symmetry. And so this actually maybe it is already has been already emphasized by Teleman, but this point of view is closely related to mirror symmetry. And maybe today I'm going to explain a bit heuristic point of view and then explain examples. And then second day I will introduce shift operator, which is a kind of quantization of Seidel representation, and then introduce reduction conjecture, which is a B-module version of the Teleman's conjecture. And in the third day, I'm going to explain its application to show decomposition of quantum cohomology B-module. So maybe you can maybe roughly speaking, it is you have Fourier analysis, then you have spectral decomposition with respect to this Fourier analysis, and then quantum cohomology D module will decompose into spectrum. So so this is a rough plan of my talk. So today, throughout my talk, I'm going to discuss this symplectic manifold is Hamiltonian T action. So I'm going to consider some torus. Just it is S1 to the L and acting on a symplectic manifold X omega. So this is just Hamiltonian torus action on symplectic manifold. Maybe you can probably generalize. You may want to generalize this to a more general Nobelian group action, but maybe torus action is sufficient for my talk, so I'm stick to this case. And so roughly speaking, so this D-module version of Teleman's conjecture. So Konstantin Teleman introduced this in ICM talk 2014, and maybe I'll explain it a bit different way, but this is close in spirit to his original conjecture. But so if you consider on one side, you consider equivariant quantum cohomology of X, T equivariant quantum cohomology of X, and the other side is a quantum cohomology of the reduction of X mod of T, and so we expect this FT stands for the Fourier transformation. So we accept some Fourier transformation relation between the two equivariant quantum cohomology and quantum cohomology of the reduction, and how they are related should be related by Fourier transformation. So on the equivariant side, you have equivariant parameter lambda I. So lambda I is a generator of the equivariant cohomology of a point. So there are L of them. So because I'm considering rank L torus, and there's new ingredient here, the shift operator or Seidel representation. So so this is all associated with co-character of a torus. So equivariant parameter is associated with character of torus, but shift operators are associated with co-character, so they are dual variables. And they satisfy certain interesting commutation relations. So maybe I write below. So this commutation relation. So lambda I, this is a relation in Weyl algebra. Commutation relation between lambda I and Sj will be z times delta ijs j. So maybe you can, if single variable case, you can write this way. So S circle lambda is equal to lambda minus Z circle S. So this means that multiplication by lambda is intertwined with the multiplication by lambda minus Z. So maybe I didn't explain what is Z here, but Z is another equivariant parameter. Maybe I write here. So equivariant parameter rotating the domain of a holomorphic sphere. But so anyway, so this commutation relation just said that this shift operator S shifts the equivariant parameter lambda by minus C. But maybe you can also see this commutation relation in a different way. So for instance, you can think of lambda as a differential operator in the S variable. So that is a somehow new point of view here. So actually, under this Fourier transformation, this equivariant parameter is intertwined with the quantum connection. So the connection in the maximum stock. So this is z times nabla qi dv qi, and so maybe I didn't say what is this direction. This direction is roughly speaking the Kawa image of the lambda I variables. So kappa is a Kawa map, the standard Kawa map from equivariant to non-equivariant cohomology of the reduction. And this shift operator is intertwined with the Novikov variable dual to kappa lambda. And obviously, on this side, this is obvious relation. So this is just the definition of a differential operator. And you have this Weyl algebra relation. And this Weyl algebra relation corresponds to the relation on this side. So this is somehow rough conjecture. So I'm going to talk about first. Maybe I start with very simple example of Fourier transformation in classical symplectic geometry. So this is, I think, well known, I guess. But consider again the action on a Hamiltonian torus action on symplectic manifold X omega, and then I can define equivariant homology. Equivariant homology is, by definition, the cohomology of the so-called Borel construction, X cross ET modulo T. So ET, this is a universal T bundle, ET to BT. This is a universal T bundle. So ET is just a contractible space with free T action. And BT is a quotient of T by T. For example, in our case, it is just BT is just a product of infinite projective space. And yeah, this is some infinite dimensional space, but you can compute the cohomology. And then under the function of this Hamiltonian action in compact symplectic manifold, then it is known that this equivariant cohomology is, roughly speaking, just an extension of the rings of the cohomology, original cohomology ring. So it splits, non-canonically splits into the tensor product of cohomology ring of X, tensor cohomology of the BT. So BT, the base of the universal T bubble, which is also denoted by cohomology, equivariant cohomology of point. And because of the assumption that I'm Hamiltonian, the action is Hamiltonian, so I have a moment map. So moment map, this is just a function taking values in Euclidean space Rn, the algebra T dual. And then, right, and then I have a Kyoto model. By the way, I forgot to say, this slides is available at my website. So if you go to my website, then you can see these slides. So Kyoto model, I have this S1 equivariant, S1 invariant differential forms, polynomials in lambda with coefficients S1 invariant differential form, and the differential is given by this. These are ordinary differential minus lambda dot iota. Iota is contraction by the S1 fundamental vector field by the torus action. So this compute this. This is a draw model for the equivariant cohomology. I think it is well known. And then I can define this equivariant version of the symplectic form, sometimes called Twister-Matt-Heckman form, and which is you can show just by the property of the moment map, and that this is equivariantly closed to form. This is equivariantly closed to form, and therefore this defines some cohomology class in second equivariant form. But this is just a preparation. Then you can see the following Fourier transformation, relation of Fourier transformation. So you can compute this something called equivariant volume, which is the integral over x of exponential omega hat. And this is a this function of lambda. This is defined maybe. So yeah, this is this equivariant form consists of actual form part and some function part. But this function part you can just exponentiate in the ordinary sense, and the form part you can only take the top degree term of the exponential omega, and just integrate in the usual sense. So this is an equivariant integral, and you can rewrite this by using the Houdini theorem, using just I can just fix a moment value mu, moment map level, fix a moment map level, and integrate over t, so which t is equal to mu. So I just restrict to the level set where mu is equal to t, and then exponential minus lambda dot mu will be exponential minus lambda dot t, and then integrate over the level set. First integrate over the level set and then integrate over t later. But integration over the level set will descend, it turns out, that to the quotient. And you see some, maybe I omit computation, but you see some classical volume of the reduction. So omega red is a reduced symplectic form. And yeah, this is just a classical symplectic volume of the reduction. And maybe if you see this formula, then you immediately see that the equivariant volume, this side is Fourier transform of non-equivariant volume of the reduction. Yeah, maybe if you particularly think of this lambda as a purely imaginary variable, then it is actual Fourier transform. And maybe I should say that here the Fourier duality is between the variable lambda. So the left-hand side is a function of lambda, and the right-hand side is a function of t. So equivariant parameter and the stability parameter t are actually a Fourier dual to each other in this setting already. So so I'm going to give a very simple example. Just x is Cn, equate with the diagonal S1 action. And in this case, so what it is, equivariant volume. Equivariant volume here is yeah, so form part will be just the volume form on Cn. So this is a non-compact example. So there's some issue about convergence. But maybe I assume that, for example, lambda is positive real, then this converges. Because the moment map is just a square root, sum of squares of coordinate functions. So this integral is just a Gaussian integral, ordinary Gaussian integral. And this will be, it can be just can be computed in a very elementary way, and just you get 1 on lambda to the n. Or alternatively, or you can perform Gaussian integral, or alternatively, you can use a localization formula. So you can compute this psi by localization, because there's only a fixed point at the origin, and lambda to the n appears at the Euler class at the origin. So this is very simple some computation. And on the other side, I have integral over the reduction. So in this case, symplectic reduction of Cn by S1 is Pn minus 1. And so I have, yeah, I just exponentiate usual thing. And this will be this. And omega red here, the reduced symplectic form actually turns out that it is a t times the standard hyperplane class. So this is easy to check. So it follows that it is n minus 1 factorial and t to the n minus 1 over n minus 1 factorial. And you see that they are indeed Fourier transforms. This is very simple, easy example, but maybe later I'll see how this can be quantized. So how this relationship can continue to hold in quantum cohomology setting. Maybe maybe probably interesting to consider the inverse Fourier transform. Here I was considering Fourier transform from the reduced from the reduction to equivariant case. But you can go backwards. And actually this backward Fourier transform or inverse Fourier transform is in a sense easier to understand. And so you can just write maybe the inverse way. So I consider the volume of the reduction as a inverse Fourier transform of the volume of the equivariant volume of X. Right. So I just apply the standard Fourier inversion formula and then get this. But now you can see some relationship to the Jeffrey-Cowan residue. So you can see that this volume, equivariant volume of X, you can write this as a sum over fixed component using the equivariant localization formula. So this will be a sum over F. It will be a sum over F, and this E of NF is a Euler classical normal bundle. And then you divide by the Euler classical normal bundle and then integrate over fixed locus and then sum over all fixed components. F stands for fixed component of the fixed locus. Then you can do this integral termwise. Now maybe something happens. So originally this function, this is a function of lambda. This doesn't have poles. It doesn't have poles in lambda equals 0. But if you write it as a sum over fixed point contribution, then each factor has poles. Each factor has some poles at lambda equals 0. And maybe you can then rewrite some each the Fourier transform of each factor, each component as a sum of residues, because it has a, maybe you can perturb this path. Maybe this path is just pure imaginary plane, but you can perturb it. And then you can write this as a sum of residues, and that is called, maybe it is not a standard one, because this maybe it involves some choice of the perturbation of the path, but you can write it as something called Jeffrey-Cowan residue, and write this as a sum of residues. So this is some classical story from about 13 years ago or so. Okay, so far it is just classical story. And I'm going to explain how this can be quantized and which is related to quantum cohomology theory. So this is based on heuristics given by Gibb et al. And so let me consider Lx tilde, which is the universal covering of free space. So Lx is the universal covering of free space. So let me, for simplicity, assume that the pi1 of x is trivial. Maybe otherwise, maybe I consider contractible group spaces, but let me, for simplicity, assume that pi1 x is 1. And then so maybe recall that you can, in symplectic flow theory, quantum cohomology of X can be introduced as a flow homology. So this was a semi-infinite cohomology of the universal covering of free space. So this is somehow relevant to our discussion. And you consider some semi-infinite cycle inside Lx tilde, which corresponds to the unit of the quantum cohomology. So there are various cycles, some semi-infinite cycle which corresponds to the element of quantum cohomology. But particularly important is the following cycle, Lx plus tilde plus. So this consists of holomorphic disks inside X. So maybe you can think of, maybe if you take a boundary of the disk, then it's a loop. So this consists of, roughly speaking, this plus part consists of loops that bound holomorphic disks. Maybe generally stable holomorphic disks, but maybe I'm ignoring some issues. This is just heuristics. So yeah, so this consists. So this corresponds maybe. In symplectic flow theory, you consider action functional, which is the most function or most spot function on Lx tilde, and this Lx tilde plus arises as some stable manifold of maybe most basic stable manifold that converges to fixed points, so it converges to constant loops. So this is a nice sample, anyway. And then what Gibb et al. Considered is the following path integral. So this square. So here, this is very similar to what we considered so far. So this is a equivariant volume of Lx tilde plus. So where omega is a symplectic form on Lx tilde, which is naturally defined by pulling back the symplectic form to loop space and averaging. And A is the action functional, just something like maybe I'm not going to give a formula, but this action function is something standard in symplectic geometry. And Z is S1 equivariant parameter as before. Here I'm considering S1 action rotating loops.
Does this mean that action functional is from moment map?
Right, exactly, yes. Yeah, action function which is actually moment map for this omega and S1 action. And then you can try to compute, and actually this is what we're going to do, and try to compute this path integral using the localization formula in equivariant homology, well, just applying it formally. And so I want to think of this as a quantum analog of volume, because this is something similar to before, and some volume of the loop space and positive part of the loop space. So if you compute this heuristically by localization calculation, then you arrive at the following expression. So this is a finite dimensional integral over x of something called a j function and some cohomology class. Maybe there's some z to the n minus half of degree z to the function, but this part may be just technical, not so important. And there's also some gamma class contribution. Maybe first explain what is the j function. The j function is a generating function of genus 0 1-point descendant invariance. Maybe I understand wrong to invariance. And maybe it is useful to note that it is the leading term is exponential omega, essentially exponential omega. So so it is kind of quantization of exponential omega. And then if you, maybe I don't explain why how this heuristic calculation has been performed, but maybe you can do this, for example, for projective spaces or complete intersections in projective spaces. And there's this gamma class factor, which maybe in the original given task computation, this factor has been dropped. But there's some infinite factor which comes from if you compute localization contribution from, for example, constant loops. So inside this space, there's some constant loops, which is also S1 fixed locus. And constant loops, the normal bundle of the positive normal bundle of X. So inside constant loops, we can go with plus. And I see. So maybe because I said positive, so maybe there's no plus here, but the normal bundle of LX plus X inside LX plus tilde appears as a localization from localization computation. And so you get something like this. And if you normalize this infinite product, you get gamma plus, we call gamma.
Does the J factor down from the bottom?
Yeah, sort of, yes. I'd say, maybe I can say, well, I say, maybe you can think of somehow, if you localize to you have somehow x0, various fixed components inside LX tilde plus, and 1, 2, 3, these parameterized degrees of the curves and conflict curves. And maybe you're counting somehow curves, connect the gradient flow line connecting to, for example, x1 and x0 corresponds to degree 1 along fixed spheres. So so this computation involves some contribution from degree D along curves, along fixed spheres. Maybe this is a rough way to say. It's not so, maybe I cannot quite explain. So. But maybe if you do this heuristic computation using polynomial loop spaces, then you see this. And so here's a nice conjecture I can make. So so because now let me define the quantum volume of X to be this quantity. So this is some defined in terms of computing variance now. And they are so if I consider the equivariant version, maybe I did here I did only explain the non-equivariant case, but you can also extend it to the non-equivariant case. So using, for example, equivariant J function, equivariant gamma class, and then that quantum volume of equivariant quantum volume of X and quantum volume of X modulo T should be related by Fourier transform. That is a naive conjecture. It is naive, as it turns out, maybe we need some bulk deformation on the other side, but maybe I should say again that the left-hand side is a function of lambda, and this is a function of T. So they are really related by Fourier transform. And yeah, so let me give just one example, two examples actually. Example one. So example one, again, let me consider X is a Cn with diagonal Austrian action. And equivariant volume in this case. Again, this is a trivial computation using gamma class, and because the J function in this case is trivial. J function is just one. So J function is just one here. And I have just using equivariant localization, you get this function, gamma function essentially. And this is maybe if you look at the pole at lambda equals 0, this will be lambda 1 on lambda n. So this is go back to the previous classical case. And let us consider the Fourier transform of equivariant volume of X. So here I put the stability parameter T to be equal to minus log Q. This is some standard way of identifying Northcross parameter with a stability parameter. And then yeah, this is just actually this is just a Milling-Barnes integral. This form, this many people are probably familiar with. And so so this function, this gamma function, has poles at lambda equal 0, minus z, minus 2z, minus 3z, and so on. And this will be a sum of residues at these points, these punctures. And I take an integration path in this green line. And then if you do this residue computation, you actually get the quantum volume of Pn minus 1. And maybe I am the computation, but this is completely elementary. So we can do this. This is one example. So this naive conjecture, at least in this case, works. And second example is a weak Fano toric manifold or orbifold equipped with a full torus action, T action, where n is the dimension of X. Okay, so toric manifold is by definition has a base torus orbit and is active by torus of the same dimension. Now, my old result says that, so this is a result on equivariant mirror symmetry, and the equivariant volume of X can be expressed as some integral representation using the given Hori-Bach mirror. And yeah, maybe somehow this is a corollary of Giventhal mirror theorem. But maybe in Giventhal mirror theorem, the cycle, this integration cycles and the gamma class part was not clear. So I showed that part. And yeah, so Wx, maybe I say Wx, the mirror Lambda-Kitzel model for X, which is certain Lorentz polynomials, given the Hori-Bach mirror. And as it turns out, this maybe in those days I didn't think of this as a Fourier transform, but maybe you can, because of this factor, you can think of this as a Fourier transform, actually, Fourier transform of this function. So And this is actually a quantum volume of a point. And here, quantum volume of a point, I think bulk the form of quantum volume of a point. So J function for a point will be like this. This takes values in the cohomology of a point. So this is just a C-valued function. And with parameters t is also values in t. And this variable xi are mirror variables, and that corresponds to the Seidel representation or shift representation. And this is has been noticed by Teleman. Anyway, yeah. So this theorem is you can think of this as an instance of Fourier transform, and this also confirms the above 9 conjecture in this case. And yeah, and actually, yeah, for toric case, I think you can prove more generally using, for example, this result, and yeah, you can prove a bit more general. So, for example, you can consider subtorus and quotient by a subtorus. You can take any subtorus and then take a quotient by a subtorus. And then again, they are related by Fourier transform. So should easily follow from this. And maybe I should say, I should remark, yeah, I think so. So in this example one, I take a kind of inverse direction of Fourier transform. So you go from equivariant volume to non-equivariant volume. But on the other hand, toric case, I consider the other way. So, so non-equivariant symplectic, so quantum volume to equivariant quantum.
There's no inequality with the other one. That is how you do this other direction.
Gamma function is here, hidden here. Yeah, so because that point has no gamma class. So that's sorry? Yeah. Yes. How it is related. So yeah, for instance, you can for example, maybe if you have such integral representation for the equivariant volume, for example, you can take a non-equivariant limit where lambda goes to 0, for example, then there's no touch this term. And then you have integral representation, and then you see that the right-hand side has some asymptotics. You can be like -3/c, where t is a critical value, maybe critical value of Wx, which is a global minimum over this cycle. As equals to 0. So for example, you can use this theorem to show certain asymptotics of the of this J. This is essentially J function times gamma plus, and so this is related to the gamma conjecture.
So do we have similarly have the quality to change the integral here, like integral or other?
Right. Yeah. Maybe you can. Yes. So one generalization of this conjecture, of this night conjecture, is to consider more general grading. So maybe I go back a little bit. So, for example, you can probably, this is a quantum volume. This is a quantum volume, but you can probably consider inserting something like chunk class of some vector bundle, and then maybe you consider like this. So E is any vector bundle on X. And yeah, so the original quantum volume is the case where E is the structure sheet. And then maybe I can say that the equivariant E and the couple of these K-theory power map, they should be related by Fourier transform. And so that more general conjecture seems to hold in these examples. For example, as you said, as you pointed out, if you consider the other grain, so other K class, then this cycle will become will be another cycle, like electric thimble. But for example, if E is an exceptional object, then this gamma E will be another electric thimble. And but yeah, so this naive conjecture still seems to hold, but then it is and also personally in this case the couple is something trivial and it's just wrong, so it doesn't matter so much. And yeah, so you can make some conjecture, but then there's some subtlety about this gamma. So there's a choice of cycles, and so only in the case where you have a structure sheet, then you have a very explicit conjecture. Okay, so maybe let me explain a bit more, much more explicit case where X is P1 with S1 action. And in this case, the Fourier buffer given to neuron is this function Wx, x plus q on x. Q is the parameter of the volume of P1. Maybe minus log q is the volume of P1. And this exponentiated potential will be I just write the definition. And if I write this parameter x as x is q to the t is some parameter, then I can write this function like this way. And maybe I will, yeah, maybe let us see what this theorem says in this case. So basically, equivariant volume will be a Fourier transform of this function. And maybe I can take a non-equivariant limit of this theorem. So I can just take lambda to be 0, so there's no such term. And then this just said that the quantum volume of P1 is an integral of this function with respect to t parameter. Because I take the x on the x, so this will be roughly speaking dt. And so this quantum volume will be an integral of this function. This is what this theorem says. And yeah, as maybe I can say that q is very small but positive number, and z is positive. Let us see. Then this function, if you look at this function is roughly of this form. So this is the graph of this function, exponential minus w over z. And maybe it is easy to see actually. So if t is negative or bigger than 1, if t is negative, q to the t will be very, very big. And if t is bigger than 1, then q to the 1 on t is very, very big. So in any case, this will be very small. So on the region where it's less than 1 and t is bigger than 1, this function is almost 0. And when t is between 0 and 1, this function may have some reasonable value or some non-zero value. Actually, it is non-zero everywhere, but it is almost zero on the reading below 0 and above 1. And between 0 and 1, it will be so because this exponent is very, very small. So between 0 and 1, it's the most 1. And if I take q goes to 0 limit, then this will be this will limit to the so-called Twistor-Hetman measure of P1. So this is by definition just a push forward of measure standard symplectic volume by the moment map to R. This is just a uniform measure. And yeah, so this is, and the classical volume is an integration of this Twistor-Hetman measure, but the quantum volume will be an integration of this a little bit weird function. So yeah, so this is somehow several tests for successful maybe test for the night conjecture in very easy case. Maybe tomorrow I will explain a bit more non-naive conjecture that maybe kind of generalization of Jeffrey-Cowan residue, but not quite, but something similar. So that corresponds to the inverse Fourier transform. And so today I will end my talk by explaining shift operators and some heuristic, again, this is a bit heuristic argument. And shift operator originally arises from Seidel's representation, 1991. And he considered for each co-character, K or ST, which defines based loop in the Hamiltonian diffeomorphism group of X. Maybe Seidel defined just generally for loop in the Hamiltonian diffeomorphism group. And this gives the map from Lx to Lx, just multiplying point-wise multiplication. So if I have a loop, gamma, I theta, e to the I theta is a parameter of the loop. And then I can multiply by k e to the I theta, just pointwise action. So this gives you a map from loop space to loop space. So you get some lattice action. So this is the co-character lattice acting on the loop space. And because as I said, this quantum cohomology can be viewed as a semi-infinite cohomology. So this map defines a Seidel should induce some map on quantum cohomology or even quantum demodulus. Okay, I didn't explain what is quantum demodulus here, but this roughly speaking corresponds to the F bundle of in the previous talk. And shift operator has been introduced in the work of Okonkov and Haipande. And there's also work by Okonkov, brother Okonkov Molik and Okonkov Molikov. And there are more recent work of generalizing this to non-abelian case by Mark Gonzalez and Pomaliano. But today I'm only going to consider abelian case. So so this is here is an example, simple example. Let us again consider Cn with diagonal S1 action. And I consider this Lx tilde. In this case, Lx tilde is equal to Lx. Lx is simply connected. It is just a infinite dimensional affine space. If I take a Fourier expansion of the loops, then this will be expanded in this way, where each AM coefficient is a vector in Cn. And Lx plus, the positive part, which balanced holomorphic disk corresponds to the positive ruling that n is bigger than equal to 0. And this is a semi-infinite fundamental cycle in the Bohr theory. Then what I want to have is some operator S acting on T cross S1 equivariant semi-infinite cohomology of Lx tilde. Okay, so T is the original T action, original S1 diagonal S1 action on X, SCN. And S1, additional S1 here is a loop rotation. You have you can rotate loops. And recall that this S is just multiplying EI theta. So this just shifts Fourier coefficients by 1. And maybe important remark here is that this map is not T cross S1 equivariant. It's not T cross S1 equivariant. You can see immediately it is not T cross S1 equivariant, but it is equivariant with respect to the following group automorphism. T cross S1 to T cross S1, lambda Z goes to lambda dot Z. So, therefore, we expect to have this relation, this commutation relation between S and lambda. So, if S were equivariant in the ordinary sense, then this should commute with lambda. But it is not equivariant in the ordinary sense. So it is equivariant with somehow twisted way. So you should get this commutation relation. By the way, S commutes with Z. S commutes with Z, but doesn't commute with lambda because of this twisted thing. Maybe you may wonder some sign, but it is incorrect. Up to the choice of the action. So let us compute the action of S heuristically again on the three-loop space or the cohomology of the three-loop space. So Lx plus same cycle, which is cut out from the original loop space by these equations. Every negative Fourier coefficient should vanish. And negative Fourier coefficients A minus M has this equivariant weight, lambda plus mz. So where lambda is a T equivariant weight and Z is a loop rotation equivariant weight. So therefore you can compute formally this class, which is given by the infinite product of lambda plus mz to the power n, and from n equal 1 to infinity. And once you get this expression for this fundamental cycle, semi-infinite fundamental cycle, because shift operator just shifts lambda by minus z, so you can see that in this infinite product expression, you can just shift lambda, replace lambda with lambda minus z, and then you get the factor lambda to the n. So this is very similar to Giventhal's original heuristic, but slightly in a different context. So you get a relation. You should get a relation in equivariant quantum D module X. So this is somehow heuristic computation of the computation, but it is, in this case it is actually straightforward to compute it by definition from the rigorous definition of S. But today I just compute it heuristically. And from this relation, it is very easy to see the following Fourier duality between equivariant quantum D module of Cn and quantum D module of Cn minus 1. So on this side, I have this relation, because S minus lambda to the n applied to fundamental class vanishes. And there is a famous quantum differential equation for Pn minus 1. So this is a famous quantum differential equation. I didn't explain this already explained in previous talk. So this is a quantum connection, F-bundle connection, and Q minus 3 times nabla Q divided by Q to the nth power also annihilates 1. So so we should have the isomorphism between the two. So this observation, so vector space case, it is very easy. It is straightforward, almost straightforward to compute, at least heuristically, this shift operator. And more generally, you can have more general representation of Cn by linear representation, higher on torus, and let d1 dn be the weights of, because there are n coordinate functions, and n coordinate function will be a character of T. So there are n weights, and each weight is an element of this lattice, integral linear combination of lambda j's. And if you consider SK action, you can do this heuristically also by rigorous computation. But anyway, you get this operator. So this is something like a hypergeometric coefficient operator. And maybe I should say, if you have never seen this, I should say this infinite product, C equal minus infinity to something, and C equal minus infinity to something. This, most of the factor cancel. So dj dot k, depending on the sign of dj dot k, either numerator survives or denominator survives. Anyway, so this is some rational expression, and this part is a shift operator. Shifting, this means just lambda goes to lambda minus kc, or maybe lambda and k are now multivariable, so lambda I goes to lambda I minus kc. And then it is very easy to see that this operator satisfies the GKZ relation. Yeah, actually, this is very similar to the story of, for example, Macbeth and Teleman, who showed the Seidel relation. The Seidel representation gives you the so-called Butler free or quantum homology toric gravity, and you get this GKZ relation. And so this relation will be the defining equation for the equivariant quantum B module of Cn. And now we know that this GKZ relation, thanks to Giventhal mirror theorem and its generalization to toric oldfold and so on, we know that the same GKZ relation defines the quantum cohomology of the reduction. So toric variety X mod of T. So you get the following picture of global Taylor modular spaces, where so here we have this quantum equivariant quantum cohomology. This is something generic object sitting in the middle, and you go to several cusps of the modular space. Maybe I'll explain how to do this in a more general setting tomorrow, but I can construct some kind of secondary fan, and this is standard in toric geometry, I think. You can construct certain secondary toric variety with several cusps, and each torus fixed point, cusps are the torus fixed points. Each torus fixed point corresponds to different choice of reductions. And because this GKZ relation defines quantum cohomology relation, quantum differential equation for the reduction. Actually, if you restrict to the formal, maybe in general, this should be formal neighborhood of each cusps. you get this quantum cohomology or quantum demodule of the reduction. Okay, so today this is the end of the talk. So thank you.